Hello, this is James Lowenberg-DeBoer from Harper Adams University in the United Kingdom, and I'd like to share with you some work we've been doing on the economics of autonomous equipment for application of biopesticides. And biopesticides have some characteristics that create some challenges for application. One of those is the fact that they have very little residual activity and hence must be reapplied at relatively frequent intervals. Another one is that they require larger volumes of water for good coverage than synthetic pesticides. This research is part of a larger body of work that is focused on looking at the economics of autonomous equipment and robotics for crop production. As you're probably aware, researchers and technology developers and entrepreneurs have very different opinions about what crop robots will look like and what kind of technology they will embody. In the sprayer case, some of them are thinking about small autonomous sprayers like the one in the photo at the left. Others are thinking about retrofitting conventional equipment. On the right is a relatively small scale tractor and sprayer that was used in the Harper Adams University hands-free hectare. In the photo here is a large scale sprayer, which also could be made autonomous, and that would solve some problems and perhaps create others. The objective of this study is to determine under what circumstances use of autonomous equipment for application of biopesticides would be profitable for farmers. The main hypothesis is that biopesticide application with autonomous equipment would be more profitable on farms that already use autonomous equipment for other field operations. So they could cover the cost of that equipment over several operations. We will focus on the control of cabbage stem flea beetle in oilseed rape. And that's because of in fact, a crisis is the best word in oilseed rape production in the United Kingdom. Until recently, OSR was the most profitable break crop for many UK arable farmers to provide an alternative for wheat and other cereals. Since 2013, when the EU ban on neonicotinoid seed treatments went into effect, there has been no effective pesticide management strategy for cabbage stem flea beetle in OSR. And as a consequence, the area of OSR in the UK has been cut in half. You can see that in the chart at the right. Not much research has been done yet on biopesticides for cabbage stem flea beetle management, but they are used in some other crops. And we think that it's important to look at, okay, can we solve some of those application questions? And that may encourage other work on which biopesticides should be used and exactly what kind of management. Cabbage stem flea beetle is an old problem, but it was made worse by the development of low glucosinolate OSR varieties in the 1960s, and they were developed to facilitate the use of OSR meal in animal feed. But by making OSR more palatable to animals, it also made it more palatable for insects. From the 1990s to 2012, neonicotinoid seed treatments were used to protect OSR from cabbage stem flea beetle. Those treatments were banned in 2013 because of negative effects on bees and other pollinators. In the past, pyrethroid foliar sprays were used against adult cabbage stem flea beetle, but resistance has become very widespread, and farmers and agronomists tell me it's not much use. Cabbage stem flea beetle damage in the UK varies widely geographically and from year to year, so it's very difficult to estimate an average. But research indicates that representative damage levels would be 5% of OSR sown area abandoned and seeded to another crop in the spring, and 10% yield loss on OSR harvested. So what are the constraints to biopesticide use for broadacre crops? Price is an important one. Most biopesticides now are marketed for high-value horticultural crops and priced accordingly. 100 to 300 pounds per hectare is common. Frequency of application. Some biopesticides must be reapplied weekly or biweekly. And then there's application volume. To achieve good coverage, some biopesticides require as much as 1,500 liters per hectare of water compared to maybe 200 liters for many conventional pesticides. Our methodology was to adapt the hands-free hectare farm linear programming model, and that model was developed to assess the economics of autonomous equipment for broadacre crops in the UK based on the hands-free hectare experience at Harper Adams. In turn, that model was based on the well-tested Purdue crop livestock linear programming model, which was used in a variety of countries in many different farm types in the US, Brazil, Colombia, Thailand, various African countries. That original hands-free hectare model was adapted in 3 ways. Number one, by including the impact of the neonicotinoid ban on OSR in short rotations, so a wheat oilseed rape 2-year rotation. By introducing a longer rotation, a 6-year rotation, which includes OSR but also field beans and linseed, and then by adding another short rotation of winter wheat with biopesticides for cabbage stem flea beetle control. And so why did we focus on the hands-free hectare model of retrofitting conventional small equipment? Well, we didn't look at the small robots developed for microspraying because they don't have the capacity to carry the volumes of water required for prophylactic pesticide use. We also didn't look at retrofitting larger equipment, which would have the water hauling capacity, but would raise safety and maneuverability questions, particularly in the UK, where the countryside is densely populated and fields are often small and irregularly shaped. We also didn't look at contractor applications of biopesticide because at current fees, that would quickly erode profits with repeat application. So the analysis shows the need for OSR alternatives in the chart. At the right, you see the bars showing returns to operator management and labor and risk taking with alternative production practices. So the one at the very left is the conventional OSR production strategies, but with no neonicotinoid seed treatments. When we add the longer rotation with field beans and linseed, returns go up a bit. And with biopesticides, they go up a little bit more. The yellow bar is for conventional equipment. The green bar is for autonomous equipment. We did this looking at a 500 hectare farm with a full-time operator. That conventional farm has a 300 horsepower tractor with a 36-meter boom, and the autonomous farm has 3 retrofitted 38 horsepower tractors with 4-meter booms with a trailed sprayer. The autonomous farm assumes 10% human supervision time for the equipment, recognizing that that's at the lower end of the estimates of the human supervision time. Some US states and the EU essentially require 100% in-field U.S. Human supervision time for autonomous equipment. Other researchers have assumed 50%, but the 10% is based on hands-free hectare experience. Both the conventional and the autonomous farm show benefit from changing OSR production practices. The higher returns on the autonomous farm are mainly due to lower equipment investment because they're using smaller equipment more intensively. The actual difference in operator time commitment is quite small. If we look at what happens as the cost of biopesticides increase, and we looked at a range from 0 to 15 pounds per hectare for product cost, and at 15 pounds, over 15 pounds, biopesticides don't come into the solution. They're not profitable. For anything below 15, the returns are equivalent between the autonomous and the conventional systems. At 15 pounds, the autonomous farm has slightly lower returns because tractor time becomes a binding constraint, and some labor must be hired. When we look at frequency of application, we find that when twice-week application is required, tractor and sprayer time becomes a binding constraint, and labor must be hired for additional drivers on those tractors. So the chart shows that with 2 times a month, so every 2 weeks, or 4 times a month every week, returns are almost the same. With twice a week application, we find that returns are reduced because the optimal plan switches. The conventional farm switches to planting some winter wheat and OSR later to make some time, and the autonomous farm is constrained by tractor time and switches partially to the longer rotation with linseed and field beans. Now, it would be profitable for the autonomous farm to invest in a 4th tractor and sprayer unit. It's a fairly modest investment, 30,000 pounds. That's not possible for the conventional farm because the bigger tractor and bigger sprayer is a much bigger investment. So the take-home message here is that the analysis shows a need for OSR alternatives. We need to change something. The volume of water required is a major constraint for biopesticide application with autonomous equipment. Even with the 10% human supervision time, operator time becomes an important constraint for the autonomous farm, especially when spray frequency increases. And for both conventional and autonomous farms, biopesticide product cost is an important factor. Thank you.